direct your questions to the chat box so that we can bring up your questions to our speaker at the end of the session. Now, without further ado, let's move on to what we all have been waiting for. Dr. Jahan, over to you, sir.
Thank you, Dr. Tushara. Can you all hear me now?
Yes, Dr. Jahan, we can clearly hear you.
Okay, then. Thank you. Thank you. Yes, thanks a lot for this opportunity. It's a great honor to talk to the University of Moratuwa students and also other attendees of this session. Yeah, thank you, Dr. Prasad, for organizing this. Yeah, I will probably move to the next slide. So in this presentation, I will introduce to this energy transformation because there are various interpretations to energy transformation. So I will explain what I meant here, what we mean here in this presentation. Then also we'll discuss about the major differences between asynchronous and synchronous generation or new renewables and traditional generation. Then there is this term system strength, which is very widely used these days. I'm not sure how far it's kind of come to Sri Lankan industry, power industry, but it's almost everywhere at the moment, the system strength, the discussion about system strength. So I will briefly discuss about what this means and also how it affects or impacts the power industry, electrical engineering systems. Then one major topic of discussion is about this inverter-based generation that we are coming across these days. So I discuss about inverter-based generation, then also challenges in all this transformation and the opportunities that we have. And also Dr. Prasad asked me to briefly discuss about opportunities for young engineers or what we expect from the industry when young engineers start working. So I'll briefly discuss about few points that we normally expect when we have a new engineer coming to the group. And feel free to probably ask questions. I don't know how that can work. Unfortunately, I can't see any of you, but feel free to raise questions while I will probably post in between slides so that you can have an opportunity to ask questions if you have any to clarify. So now we all know this, traditional power systems are dominated by synchronous generators. Normally in Sri Lanka, we have a coal power plant and then plenty of hydros, but no nuclear in Sri Lanka and not in Australia either. Then there are plenty of gas turbines. Almost all of them are synchronous machines. So that's the traditional power system where most of the generation is by synchronous generators. But now what we are seeing in maybe the last decade, there are lots of renewable generation, mainly solar and wind, penetrating the system. One issue with them is they are asynchronous, or they are mostly inverter-based generation, or induction machines sometimes if they are wind turbines or wind turbine generators. And on top of that, what we are seeing is retirement of synchronous generation or decommitment of synchronous generators. That means most of the time, because of lots of solar and wind in countries like Australia, we see coal generators retiring because they can't really compete, or that's not economical for them to be in the market. So they gradually, or when their lifetime is completed, maybe 50 years, then rather than renewing or refurbishing the plant, they just decide to retire the plant or decommission them. Then the other term is decommitment. It means if you have lots of solar or wind running, there may not be a reason to run hydro or other gas turbines in the system because there is a certain load. If you have a certain load, if most of the load is supplied by solar and wind, you don't need much hydro or gas to operate, or even coal. So that's the decommitment. That is, you have the generators available in the system, but there is no need to run them. So modern system, most of the systems these days, you find that there are less synchronous generators in the system compared to 10 years ago, 20 years ago. And if you look at the forecast generation capacity, now I have looked at I have got kind of forecasts, one for Australia and one for Sri Lanka. This is for Australian national electricity market, where it forecasts. Can you see this one clearly? This plot, is it okay?
Yes, sir, we can see it.
We can see
okay.
Okay, so it's coming up well. Yeah, so what you can see is now you have black coal. We can see with time by about 2040, the level of black coal generation can probably reduce from about 20 gigawatts to about 5 gigawatts. That's the kind of expectation. Then similar with brown coal. Then hydro, you can expect similar levels to remain. But if you look at solar and wind, the yellow ones, lots of solar is expected in about 20 years' time. Already there are a significant amount of solar in Australia, but in 20 years' time, you expect that to increase significantly. It's same with rooftop PV. You can see that's the residential solar mostly, and then wind as well. So what you can see is more than half of the generation can be asynchronous generation in 20 years' time. And this is again, now I have mentioned that this is a central or neutral scenario, because when you do a forecast, I think you might have probably not have come across that. Maybe those who are in electricity board, who are doing generation planning or system planning might have come across. We assume certain scenarios. It can be a central scenario. It means normally based on the present policies or present trends, that if you assume present trends to continue, all the government policies, public perception about energy and demand growth, prices, technology developments, this is the kind of picture that we might see in the next 20 years. Then there are other scenarios as well. You can, if you refer to all these planning documents, you might come across a fast change where you can expect sometimes some governments encourage people to adopt more renewables, or some governments encourage people to go for more coal. So it depends on the government policies sometimes. It's same with people or technology developments, especially grid battery storage. For example, at the moment, it's very expensive, but in 10 years, 20 years time, we expect the battery storage to become very cheap or comparatively cheap. So that can be more available, freely available. It's same with solar at the moment. 10 years ago, it was very expensive, but now it's very cheap compared to other forms of generation. So you can assume different scenarios. So if you assume central scenario, this is what you can expect. Then if I move on to the next picture, this one I got from the generation expansion plan of Ceylon Electricity Board. You can find this on their website. And this is their base case. Base case is similar to a central scenario, where you assume, okay, this is the kind of present thinking or the present trends. This is what you expect. So Sri Lanka situation is slightly different, because it doesn't look like there is a plan to, say, get rid of coal, because you can see coal is gradually increasing. That's the kind of present thinking. Hydro kind of remains same. Then combined cycle, that is natural gas kind of generation, you can see it's still expected to increase a lot in 20 years' time. Wind, again, expected to increase. Mini hydro somewhat remain the same. Solar expected to increase. Major hydros, again, expected to, major hydro is the first one, it's mostly remain. And you can see the peak demand also indicated in this plot. So what we can see is, still in Sri Lanka, you expect lots of traditional synchronous generation, but significant amount of solar and wind as well in 20 years' time. So what's the problem? Why this high asynchronous generation is an issue, or why people are talking about it as something that we need to think about? It's mainly because of the difference between the type of generation, synchronous and asynchronous. If I go to the next slide, yeah, this is another slide I just put in to show what's happening, expected to happen in Australia in the next 20 years. You can see lots of solar and wind is expected to come in. but negative values are kind of decommissioning. You can see coal and mostly brown coal and black coal is expected to drop. And then also some gas turbines is expected to be decommissioned. But you expect to see more storage, wind, and solar, and distribution storage as well. Distribution storage and wind, and also residential solar PV. So that's the kind of expectation. That means you expect lots of synchronous generation to go away and more asynchronous generation to be available or connected to the network. And why is this happening? We all know one is the intervention of the governments, because some governments are very actively moving towards renewables, especially in the Europe and UK, USA. You can see if you have read about their industry documents, there is lots of encouragement for the industry to move towards renewables, mainly because of the worries about global warming, emissions, environmental concerns, all these things. It's somewhat similar here in Australia, where there is lots of public perception that the government should do more to encourage or promote renewables, mainly solar and wind. So that's one reason. And then also, I have another slide, next page, about the cost of new generation. What we are finding is solar and wind have become very cheap these days compared to building a new coal power station or new hydropower station. So that's another reason, because if you can develop the same amount of, say, generate the same amount of megawatts by spending less money, people will always invest on the less cheap generation. And the other one is people or public perceptions, because some countries, they are very keen to be using less emissions technologies. So they most of the houses here, for example, have residential solar now. So that will cause additional issues because we have lots of solar generation in the distribution network. I think it's happening in Sri Lanka as well. Yeah, so this is the cost of new generation. This is called levelized cost of generation or energy. That means what is the average cost in dollars per megawatt hour to generate, capital plus operational cost. You can see solar is very cheap, about kind of $50 now these days. Wind, similar range. Then you have hydro, then come gas turbines. Black coal now becoming expensive because building a black coal power plant is a huge exercise. So it's normally expensive compared to solar generation. And if you move towards to the right, you can see this very expensive one. This is called RERT. This is something in Australia. I don't think it's available in Sri Lanka. This is kind of contracting loads to shed themselves. Because suppose if there is a peak, very high demand day, if you don't have enough generation, what sometimes utilities do is you go and pay some major industries to shut down on that day. So they are paid a lot for shutting down because then you can reduce the demand and you can avoid load shedding in the other areas or major load centers. So, but you have to pay a lot for that. That's called RERT normally. Those are contracts. And then you can see what else? Battery storage, still expensive, but it's becoming very cheap now. You can see 10 years time, you can expect these prices to drop a lot. Do you have any questions up to now? No? Feel free to ask questions if you have any.
So what are the storage methods that are using currently in Australia?
Now we have mainly it's batteries like normal lithium ion or Tesla batteries mostly. Then we have hydropower storage as well. There is a big hydropower station or pump storage station being built at the moment in Australia, in New South Wales, in fact, about 2,000 megawatt capacity. And there are a few storage hydro stations where they have some storage where they pump, say when the price is low, they use pumps to pump water to a higher level reservoir and then use that water again when the price is high. So they are kind of like, say, not an efficient system because you use pumps to pump up water and then use that energy stored, again generate, but they use the price differences in the system because we have an electricity market where price changes every 5 minutes kind of. So if you have high prices, especially during evening peak, the price gets very high because of the high demand. But there can be times where, say, around in the morning, in the afternoon, price can be low because there is lots of solar generation, or even overnight, price can be low because demand is low. There is enough generation, so the price will be low. So those times, what they do is they go and pump water from downstream reservoir, ponds to upstream reservoirs, and then during the high demand time, they generate. High price time they generate so that they can still have a profit. So hydro storage and then batteries. Batteries becoming popular now, still not very much in use because still expensive. But now most of the solar farms and wind farms, they come with the battery as well, because what they do is when they have excess generation, they charge the battery. And then again, when the price is high, they use the energy stored in the battery to generate and have a higher income. Any other questions?
And it is Anuraj Pala.
Hi Anura, how are you?
Yeah. No, I was referring to this coal issue. You know that Sri Lanka, although we have one power plant, say 1000 megawatt or 900 megawatt, and planned another couple of power plants of similar scale, the present consumption is about 2.5 million tons. So even if we triple the capacity, it will be about, say, under 10 million tons. But in the world perspective, about, say, 8,000 million tons a year, it's quite a different scale. And I find in this thing that Australia is producing about 500 million tons a year and export most of it, 75% of it.
Yeah.
So they are different scales. So even though Sri Lanka is doing a couple of coal power plants, it is almost zero coal power plants in the world standard.
Yes, agree. That's true. Okay. Yeah, but now, if you look at even Australia, in about 20 years' time, we expect maybe there may be only 1 or 2 coal power plants in the whole name.
But what about are they going to shut down the coal mining? That is 500 million.
That's the question. That's the question. Probably it's more political question.
Whether they burn or produce, all the same. It's because climate change is a global issue.
Agree,
so whether they burn it in Australia or produce and burn somewhere else, the same effect.
That's right. But there is pressure as well now. There is political pressure to shut down gradually coal mines. So that could happen as well here gradually.
Yeah.
So there is lots of discussion about
those are big financial issues. 500 million tons is quite a big.
That's the case. That's right. Yes.
Yeah. Sorry to have disturbed you. Okay, go ahead with your presentation. Okay.
No.
Okay.
That's good. Thank you.
Okay.
Yeah. So let me. If there are no more questions, do we have any other questions? Anyone? Let me move on then. Yes. So this is just a comparison of renewable or asynchronous generation compared to synchronous. So one major issue is they are not dispatchable. You all know, say, they generate, say, solar farms generate when the sun shines, or wind farms generate when wind blows. So the problem is if you don't have enough storage, then there could be reliability issues where when the demand is high, if you don't have enough generation, you have problems in supplying the demand. Even now in Australia, there are days where in summer, you have to ask some major industries to shut down their plant because you don't have enough generation to supply the demand. Because if unexpectedly, it can be a hot day but cloudy day, still the demand is high, but there is no wind sometimes, especially in summer. There can be, during daytime, wind is much less compared to nighttime. So you might have issues with supplying the demand load. So reliability is the main issue sometimes if you don't have much dispatchable generation. And on the other hand, it can be the other way around as well. If you have lots of solar, especially with residential solar, huge amount of residential solar, you might find that you don't have much demand or load to supply. So you have excess generation sometimes. And one other issue is the inertia contribution, because synchronous generators, we all know, contribute inertia to the system. And inertia helps with frequency control. Higher the inertia in the system, when there is a change or disturbance, the frequency change takes time. So, but with residential solar or even other utility solar and wind, normally there is no major inertia contribution. But things are changing. Now those technologies are picking up. I am talking more about the traditional inverter-based generation where it's more grid following. But now people are talking about grid forming inverters, machine modes, and like that. They are working on running the asynchronous generation like synchronous machines. So it's happening, but right now it's a major issue, the inertia loss when you reduce synchronous machines in the system. It's same with fault current contribution. There are synchronous machines. Normally we know we have about 4 or 5 times the rating. If a 100 MVA or 100 MVA synchronous machine, if there is a fault, you can expect about 500 MVA fault current or fault level contribution. But asynchronous machines, or solar farms, wind farms, you hardly see more than its rating as the fault current contribution or fault level contribution. So the problem is if you don't have enough fault currents, when there is a fault, sometimes you struggle to detect the faults, especially if you are relying on overcurrent protection, especially distribution systems or low voltage systems where you rely on overcurrent protection. But there are solutions for those as well. Sometimes you can look at differential protection and like that. So there are solutions, but they are expensive solutions sometimes. Then the other issue is voltage control issues, especially if you, during faults or just after faults, voltage recovery. Synchronous machines help that much more than asynchronous machines. Then one other issue is this ability of the generators to ride through faults, or what we say is we say that they rely on most of the grid following inverters, or existing or present technology solar farms and wind farms. They rely on the grid for their stable operation. They are called grid following inverters mostly, or we relate this term system strength to that. System strength is more related to, I will go through, I have a couple of slides talking a bit more about system strength. Now, for example, solar farms, for stable operation, you need to have a certain level of system capacity or system strength or a fault level. It's called SCR. I will define that later on. So what happens is when the system strength is low, you might see fault ride-through issues. So instability of solar farms or wind farms. If there is a fault, sometimes they can't manage stable operation. They might trip or they might struggle to maintain stable operation. It's same with, sometimes there can be interactions with other plant. We have seen that in Australia many times, many places, where nearby solar farms and SVCs sometimes interact with each other and create oscillations, unstable or poorly damped oscillations. So those things can happen when you have lots of asynchronous generation with very low fault levels in the system or system strength. And another issue with these renewables is the location, because most of the established grids are near the synchronous generators. Even in Sri Lanka, I think there are more transmission lines coming from the hydropower stations. There are lots of transmission lines to the load centers near Western Province from the hydropower stations. But if you go to Hambantota or even up north, the number of lines you see is much less. So there will be a cost for new transmission. And also the problem is if you look at the location, resource location, sometimes the best location may be not near the load center. for example, wind farms in Sri Lanka, southern province may be the best location in Hambantota area, but you don't have much transmission. So you can't build a 1,000 megawatt plant there, wind power plant, because you don't have transmission. You will have to build transmission as well. So that will add to costs. And yeah, this is just some description about system strength. Now, this term, I don't know whether it's widely used in Sri Lanka these days. It's normally related to fault current. And we all know fault current is normally three-phase short circuit capacity is referred to as fault level. Then if the fault level at a particular location is high, we call it as a stronger system or stronger location from system strength point of view. And it's obvious system strength at a given location is usually determined by, if we have a number of generators, synchronous generators nearby, the fault level will be high. If you have long transmission lines, fault level will be low. And if they have multiple lines in parallel, the fault level will be high again. So the system strength is similar. Or effectively, it's in theoretical or in mathematical terms, it's the Thevenin impedance. High impedance means a lower system strength or lower fault level. Other way around, if you have a very low impedance from the source to the point, then it will be a higher system strength location. So this is just a map of New South Wales power system. If you look at this, is in the north you have Queensland, in the south it's Victoria, and to the west it is more South Australia. And Sydney is around here, where this I have indicated as a pink circle, that's around Sydney. We have so many lines. You can see 500 kV lines, which are the yellow ones. 330 kV ones are the orange lines. And there are a number of power stations. You can see number of coal power stations near base, sort of these green squares. And then also Eraring, Wells Point, and like that, they are coal power stations. And then Mount Piper. So many coal power stations near Sydney, and many lines as well. So if you calculate the fault level near Sydney at the bus bar, it's about 15 GVA or 15,000 megawatt MVA. So a fairly high fault level or fairly strong location. But if you go further away to the west, where I have marked as in these green circles, they are very weak locations. Now you can see this line from Broken Hill to Bironga. It's about 250 kilometer long, 220 kV line, one single line. So, but we have lots of wind and solar generation in this area. But so what we can see is fairly weak system strength point of view, or fault level point of view, less synchronous plant. There, you don't see a synchronous generator until you come to around Vaga, this Urangrindi power station. So all this is about 250 kilometers to Bironga, and then the line from Bironga to Darlington Point is about 400 kilometers. So it's more, if you compare with Sri Lanka, it's almost wider than Sri Lanka and longer, almost similar length to Sri Lanka's. We have only one line, 220 kV line, but lots of generation in this area, solar generation, because it's a very dry, heavy irradiance area. Then if I just found a map of Sri Lanka as well. And here again, I can see, we know most of the generation is here in the hill country near Western Province, where we have lots of gas turbines and hydro generation. So we should calculate the fault levels comparatively to other locations. Fault levels will be high here. So system strength point of view, it will be much stronger in this area. But if you move away, you can see only one 220 kV line or 130 kV line towards north, and a few 130 kV lines towards south. So if you calculate fault levels, will be much less compared to near the Western Province or in the hill country area. So system strength point of view, you will have weak system strength towards south and north of the country. And so why this system strength matters? As I mentioned earlier, there are a few issues from physics points of view, or when you operate the power system from power systems point of view. One is lower the system strength. That means effectively it's lower fault current, so there can be protection issues. And not only that, you might have already studied this or come across this one. If you have a high fault level location or high system strength location, when you switch in, switch out reactive plant, the voltage change is much less compared to a weak fault level location. Normally, you can rule of thumb is if you have a say certain fault level, say 100 MVA, if you have a 20 MVA capacitor, normally 20 over 100 will be the voltage change when you switch in that 20 MVA capacitor. So 20% voltage change you can expect. But we know a 20% voltage change when you switch in a capacitor is not accepted. Normally, you would not expect anything more than 3% normally in Australia when you switch in the reactive plant. So that's another issue with fault level. So you might see that as well. No? When you come near the high fault level locations or stronger system locations, you see larger reactive plant. Even in Sri Lanka, if you go and check, say near Western province, the capacitor sizes may be larger compared to far away. If you look at Anuradhapura, Jaffna, or Hambantota, the other reactive plant sizes, capacitor sizes should be smaller. It's because the voltage change you expect is much less compared to a stronger location. It's same in Australia. Like say, if you have a 330 kV system, you have 200 MVA capacitor banks sometimes. But 220 kV network, we have only 10 MVA, 20 MVA capacitors. It's because of the voltage change that you see when you switch in the reactive plant. So one is, that's another issue. Lower the system strength or fault level, voltage change can be higher. And it's same with the voltage angle change. If there is a generation tripping or line outage, low system strength locations, you see a larger voltage angle change compared to a high system strength location. So what happens is that means when there is a large angle change, the voltage angle can move towards the unstable region easily. So this can be a problem in low system strength locations compared to high system strength location. And so what's the issue with this integrating power electronic generation? One is, as grid following inverters, most of the power electronic generation or solar farms, wind farms, they rely on inverters to connect to the AC networks. But they rely on the grid for correct operation. Inverters, they have this phase lock loop that relies on the system. That relies on the system voltage profile for satisfactory operation. So if you have a low fault level location, the grid voltage can change significantly for the disturbances. So the inverter struggles to maintain stable operation. So this kind of assessment is presented as the short circuit ratio requirement. It's defined as 3-phase fault level divided by plant megawatt capacity. Say if you have a solar farm, for example, is in this example, suppose if you have a 500 MVA bus bar and 100 megawatt solar farm, we define the SCR as 500 divided by the capacity 5. Normally, what most of the inverter manufacturers say is, if you have a SCR of 3 or above, they expect the inverters to perform correctly under various contingency conditions. But if it is less than 3 or even less than 2 or something SCR, they say probably you might have to do studies and model and see what will happen. They don't guarantee. Normally, if it is less than 2, normally they don't guarantee correct operation for different contingencies. Because normally if there is a fault in the system, you don't expect the solar farm to trip as well. Normally hydro generators or the thermal generators, they don't trip unless the fault is very near the solar generator, or unless the fault is within the generating system. You don't expect the system generators to trip for system faults. unless it's a very bad fault, which is not cleared for an extended period. But solar farms and wind farms, they might struggle sometimes. If the connecting location is very weak, we find that for some faults, they can't ride through. They will trip by themselves. So they normally, inverter manufacturers, they specify a SCR level. Typically, it's around 2 at the moment. They say above 2, they are confident they will not trip. The inverters will be able to ride through a fault. But below 2, they suggest us to do more studies. And in this example, now if you have a 100 megawatt plant, we have a SCR of 5. But if you add another 150 megawatt plant, now the SCR will drop to 2.2 because we have 250 megawatts now. Still the fault level remain the same because if you have, these are asynchronous generation, so the fault level contribution is very much negligible. So normally you use the synchronous fault level, which is 500 still. So divided by 250, so you end up about 2 as a SCR. Now, if the inverter manufacturer says their plant can withstand the SCR of 2 in their inverters, then we are okay. We don't really have to worry too much about this. But sometimes they might say, no, below 3, we can't guarantee stable operation. So what we normally do is we use this SCR as a screening tool. Whenever we get a new connection application, we check what is the current fault level, what is the present generation, asynchronous generation connected, like in this example. Then we add the new generator. If the result in SCR is less than 3 normally, we suggest you have to do more detailed modeling. Often we use EMT, electromagnetic transient simulation software. Often these days it's PSCAD. Sorry, it should be PSCAD, not PC. Yeah, it should be PSCAD. I think most of you are familiar. I think you have it, that software application in the university. Any questions so far?
Now, Jahan, this your system, just like an island like us, much bigger island, of course. And how much they maintain reserves, running reserves?
Now, yes, we have actually FCAS market, frequency control and civil services market.
Okay.
Now, normally we maintain FCAS to cater for, there are different FCAS levels. Now, in the FCAS market, there are 4 kind of FCAS categories. One is called regulation reserves, which is normal to maintain the frequency near 50 hertz. So depend on the load changes or little generation changes, little small changes in the system to ensure frequency remain at 50 hertz. They have this regulation market. So they dispatch few generators to ensure that they look after the frequency around 50 hertz. Then we have contingency reserves where we cater for largest generator or load trip. Say,
are they rotating reserves or hot reserves?
They are all rotating online.
Okay.
So continuous reserves, that means we have largest generators about 750 megawatt in Australia in the NEM.
Okay.
We have reserves for regulation reserves. Also, there are 3 kinds. One is fast reserves because you have to maintain under the Australian national electricity rules. There are frequency requirements. If there is a large generator trip, you are not allowed, the frequency is not allowed to drop below 49.5 hertz. Okay. So it can happen in about 2-3 seconds. So you have to, that means make sure that you have enough generation added within that 2-3 seconds to make sure frequency will not drop below 49.5 hertz. So we call that as fast reserves. Then we have, that is normally 5 seconds.
Are they kind of hydro or thermal?
It can be both. Mostly,
Both.
sometimes it's high, because sometimes there can be times where we don't have any hydros running in the system. Often it's the case, because hydro you don't normally run as base load generation.
But the question is, if it is gas turbine, they have to be single stage, isn't it?
Yes, that's right. That's right.
Yeah.
And it's
not
mostly
not
thermal.
combined cycle.
No, that's right. Yeah. And so it's thermal at the moment, but things are changing as well. So we have 3 continuous reserve categories: 6 seconds, 60 seconds, and 5 minutes. 5 minutes is more longer term. Okay. Yes, because 6 seconds is mostly to keep the frequency captured within 49.5. And then 60 seconds is normally, you know that some generation, they provide the boost of power, but they can't sustain it. But some generation, they can't give that boost quickly. So you have 60 seconds picking up gradually when that fast generation drops out. So they have a market here for that as well, FCAS market, frequency control and services.
Okay, thank you, Jahan. Okay, go ahead.
Any other questions? If not, I'll probably move on. Yeah, so these are few practical issues that we have come across in low system strength areas. One is the sustained voltage oscillations. Now, for example, this happened during a planned outage where under system normal, the SCR is about 6. But when you take out one line, this is actually in this system. I will show you the location. Here near Broken Hill, this happened near Broken Hill. If you look at, there is one line, 260 kilometer long line from Bironga to Broken Hill. And then there are another line to Bironga, 1 220 kV line, 2 220 kV lines. So this line was out of service. Then what we noted is there were oscillations. In fact, actually, we haven't modeled this. When this happened about 4 years ago, this incident. We didn't do any PSCAD modeling during that time for these kind of operational or even connections. But people working at the substation noted some flicker, kind of lights flickering. Then when they called the control room and told there is a problem here, and then they noted there are oscillations, voltage oscillations happening in the system. So because we have a SV, there is a SVC and a solar farm at Broken Hill at the time. So they were interacting with each other and causing this oscillation. It's about 8 Hertz oscillation because of that low system strength situation. So what they did was the operators immediately put the SVC in manual mode. That kind of settled it, or it removed oscillation, because when both are trying to control the voltage, or when they are both in automatic control mode, they can interact. But if you bring one into manual mode, then that interaction will go away. But what we found later is you can model this. You see this in modeling. Say when we create a PSCAD model of the system, when you have system normal operation, you don't see this oscillation. But when you take one line out in the model, you see this oscillation. So these can be easily modeled and seen. And there is another one. This is a similar one, same location. Again, these are PSCAD studies because we had another wind farm coming to the same location. So what we found is under system normal, or with only first plant, we have about SCR 5 or 6. But when you add the second plant, SCR drops to about 1.4 because you have to add the megawatts of the 2 plant, then you have the same fault level. Short circuit ratio drops significantly. And the existing plant inverters, they say their inverter technology is very old, so they can't operate in a stable way if the SCR is less than about 3. So we can expect a problem if it drops to 1.4. But the second plant, wind farm, it's the same kind of a type 3 inverter, that's DFIG, doubly fed induction machine kind of inverter based generation. What they say is they can operate in a stable way if the SCR is more than 1.2. Wind farms are quite good, especially type 3 wind farms. So those DFIG machines where they are not really pure inverter based. I think you might have studied all these. Type 4 has an inverter interface, so it's completely power electronic interface. But type 3, you have a partial interface, so they can operate in low system strength areas much better than type 4s. So what these wind turbine generators said is, they can operate if the SCI is more than 1.2. You can see in the middle plot, you can see that what's happening is that when you model it, the second plant can maintain stable operation. But the first plant, it goes through this repetitive fault right through. What's happening is, it finds that when it is generating, the total SCI is less, so it's kind of blocking its operation. Then the megawatts drop, and then the system seems to be fine now, because what inverters do is, when there is a system issue, voltage issue, it blocks itself. And when the system voltage recovers, it starts to operate again. So it blocks, then it only sees the other plant in the system voltage becomes better, then it thinks our system is fine now for me to go get wind. So it starts operation again, but it can't sustain, then it goes back to fault right through mode. So we call this as repetitive fault right through. So this happened in modeling, and we saw that in practice as well, because we did some testing to check these models, and we can see this in practical systems. So it's very important now. These days, we do lots of PSCAD modeling when we connect new generators. So now, I have tried to summarize these things as challenges. Now, especially when we have high penetration of high asynchronous renewable generation, which is normally at the moment solar and wind, and along with what we see is retirement of synchronous generators or decommitment of synchronous generators. So as we discussed earlier, there will be supply reliability issues or not adequate generation. That means you might end up load shedding. It has happened most of the summers here. It happens now because of that. Or at least you will have to ask industries to shut down, especially aluminum pot lines, which has about 300 megawatt pot lines. There are contracts with them to shut the plant down for a couple of hours without any serious issues for their production. So you shed load when there is not enough generation. Then, as we mentioned, frequency control is the issue, especially because of the system inertia reduction. And this is a major issue because there can be failure of under frequency load shedding. If you don't have enough inertia, frequency can drop. If there is an incident, frequency can drop significantly faster compared to if you have high inertia. Then we normally in the system, you have under frequency load shedding to capture unexpected faults. If you can't sustain the frequency, or if there is not enough generation to match the demand, what you do is you have a number of loads selected to go and shed or trip. But those relays need some time, about few hundred milliseconds to do that shedding process. But if the frequency drop much quicker, under-fixed load shedding will fail. So frequency will continue to drop, and you will have a kind of a failure, cascade failure, and you might have a blackout. And other one is inability to cater for contingency. Multiple contingency is a major issue. You might have heard that we had the blackout in South Australia maybe about 3 years ago again, where they had number of faults in the system because there was a severe thunderstorm, number of faults, and then number of wind farms tripped as a result, because wind farms kind of struggle to keep stable operation, so they tripped. As a result, there is one interconnector from Victoria to South Australia. The power flow on that interconnector significantly increased, so it tripped as well. But the remaining system had under frequency load shedding, but power imbalance is too much. The frequency drop became very severe. So the whole system became black within a few seconds. So catering for multiple contingencies could be very challenging if you don't have enough inertia in the system. And another issue is with the asynchronous generation is we know they don't contribute much fault level to the system or system strength to the system. So having high penetration of system asynchronous generation means you have much continuing reduction of system strength. So that could lead to dynamic plant instability and also control interactions, as we have seen, as we discussed, which could lead to flicker issues. And all these things lead to more extensive studies, mainly now these days PSCAD modeling. And I think if you have used PSCAD, it's a way, because they use very small time steps, often microsecond kind of time steps, 6 microseconds, 10 microseconds kind of time steps. So very time consuming to do a simulation. And one other issue we have in the Australian industry is shortage of experts to run PSCAD. So at the moment, we are going to almost every country for doing the studies consultant. Like say we are consulting Manitoba, then Manitoba Hydro, MHI, that is Manitoba Research Center, Hydro International, that is HVDC Research Center, and then Hatch, the number of consultancies around the world, because we don't have enough experts in Australia to run these simulations at the moment. Before I go to that one, any questions on this one, like say mainly issues with the asynchronous generation? If not, I will move on. Then what are the opportunities of these renewables? One major opportunity is the lower cost of the generation. And it depends on the location as well, because if you have to build transmission to support a new generating station, it will add to cost. But generally, very cheap these days, solar farms and wind farms compared to building a new gas turbine or a coal power plant or hydro station. And reduced emissions. I know lots of discussion globally about global warming and emissions, reduction of emissions. So having more renewable generation, especially solar and wind, reduce emissions. And one other thing is shorter lead times compared to coal and large hydro projects. Normally here in a solar farm can be built in a year now these days. It takes another year or two for the approvals, but when they start building, they will complete the construction within few months, 500 megawatt solar farms and like that. Then also from your point of view, especially those graduating electrical engineers, those engineers with power systems knowledge, power electronics knowledge, especially about inverter controls, grid forming inverters, knowledge on battery storage, then protection systems, control systems, and power system applications like PSSC, Power Factory, and in particular PSCAD, and programming skills, Python, MATLAB, have a very high demand. I think could be similar in Sri Lanka, but over here, power systems engineers are very valuable resource these days. Any questions? If not, I have one more slide. This is Dr. Prasad asked me to just mention about few things that probably industry expects from new engineers, not only new engineers, any engineer or even any employee. Normally, yeah, we would expect them to be very proactive. Normally, like I said, don't wait to be told, because these days we don't have much time to supervise young engineers. So it's good if they can be proactive and kind of initiate themselves and also be reliable. That is, ensure you perform what is requested or expected. Don't wait to be reminded, because if you have an engineer, if you need to be reminded all the time, it's kind of a burden for the senior staff. So make sure if you are asked to do something, just make sure that you perform the requested task. If you have a problem, just tell them in advance. And also be thorough, because that's another thing that we are finding very valuable, because especially young engineers, sometimes they want to just finish the job quickly rather than doing a good job. So don't wait for the reviewer to check. That's the other one, I think. Try to be accurate as well. Ensure your reports or study results has minimal errors or no mistakes. Don't rely on the seniors to check and correct. Then another one is attitude. Try to have a positive attitude or can-do attitude. Don't try to be negative. And be prepared to accept responsibilities as well. That is, if you are in a meeting, if something comes up, if someone asks who can do this, feel free to raise your hand. Yes, I know it's more extra work, but normally it's good for your career development. And be a team player, collaborative, friendly, help others, not try to be selfish, because sometimes in the longer term, if you give credit to someone else or help someone else get credit, it will help you in the longer term anyway. And another one is don't be afraid to accept mistakes, or you can learn from that, and also ask questions. Don't be afraid to ask questions. Make sure that you ask questions, understand it before you go and start doing it, because sometimes what happens is you talk to someone, say young engineers, you tell them something to do, but they will understand it in a different way. They go and do completely different thing that you expected. Then it wastes your time as well as their time. So it's better if you ask the question and I understand exactly what you are expected to do. That will help as well. And there may be many others, like try to continue your development. Don't think, I know most of you are final year graduate students. So don't think after graduation everything ends. Probably it commences then. Yeah, all the best with that. And yeah, if you have any other questions or if you want to discuss about anything else. Okay, that's it. Yeah, thank you for your time.
Jahan, can I ask one more question?
Yeah, no problem.
No problem. Now, your design criteria is for multiple contingencies, N-1 or little more?
Yes, Andre, it's N-1, like say.
N-1.
N-1, we have a slightly different reliability criteria. So system security criteria is N-1. That is if in the event of any
load probabilities.
Yeah, that's the reliability criteria is we have slightly different way of defining it. You are given a little bit of unserved energy kind of margin these days. So that means a first contingency, we can shed some load, but there is a limit. Per year, you are given, say, certain number of minutes, say 5 minutes of average load. Say, if you have a certain substation, suppose 100 megawatt substation, we are given 5 minute unserved energy capability. So that means we can drop 100 megawatt for 5 minutes during a year. But if anything more than that, we are kind of breaching the standard. Because it's a more economic standard now at the moment. It's because if you try to ensure 100 megawatt all throughout the year, if there is no unserved energy kind of availability, then it will be very expensive for us to keep the system maintained. You have to, especially because
what is the word you use for that expensive, that the agreed shutdowns for a day or something? You used a word for the tariff slide. That brown color tariff slide, you said you used a word.
RERT. That is
what is
it's called reliability and emergency reserve trader contracts. Reliability and emergency reserve trader contract. It's more. It's a Australian energy market operator has the right to get into contracts, because there are different. Now, even we have contracts with industries. We call them as demand management. What we do is, because especially short term, say if we expect, suppose if we have a substation, 2 transformers, say 100 megawatt transformers, demand is, say at the moment, say 90 megawatts, so we are fine. If one transformer trip, we can still supply the demand. But if due to demand growth, if say in 2 years time demand is going to increase to 110 megawatts, then we have a problem, because we have only 2 transformers, 1 trips. We have 10 megawatt deficit, or we have to do something to avoid that the other transformer overloading. Then in that case, either we have to shed that load or bring in another third transformer to make it okay. Then what we can do is we can enter a contract with the industry. We can say if the demand is more than 100, we pay you, can you shut down? Say we might enter an agreement with another industry to give a 10 megawatt kind of benefit for us. So what we do is we pay them. So industries or the transmission utilities come into those contracts. In addition, AEMO, Australian Energy Market Operator, can go into these contracts.
That's a new concept that we can also use here, you know. That
I think so. That's
something new.
So that is the demand response kind of thing.
That's right, demand response. But what we are finding is it's more expensive in the longer term. So what we do normally is we have, for a couple of years, we enter into those contracts because then you pay them. It can cost millions sometimes. But then 3 years later or 5 years later, we bring in a transformer, we bring in a transmission line. Sometimes bringing in a transformer or transmission line can take time. So during the time that requires to build that, we enter into a contract with another industry, a demand management or demand response contract. But it's what we are finding is very expensive compared to a longer term solution, because industries, they have to kind of cope. It costs them
their
as
obligations.
well.
Yeah,
That's the case. They have to.
So
that costs them.
Yeah. Other than this demand response, are you practicing the curtailment as well?
Sometimes, yes, because sometimes we have to, because if we have.
So is it for the renewable or is it for any other?
I noted that under frequency load shedding in your slides.
Yes. We have under frequency load shedding, but normally under frequency load shedding starts only when the frequency drops below 49 hertz. So we can't shed load because now there are, under the rules, there are few contingencies that we can't shed load. Say for a single generator trip, we can't shed load.
Shedding is for the load side, but for the generator side, we are going for the curtailments.
Lots of curtailment. Like if you look at this slide, because we have in this area, say for example, we have Balranal about 450 megawatt of solar generation. At the moment, we allow only about 150 megawatt to generate at a certain time. Because what happens is this line is very long, about 250 kilometers long line. If you have more generation, the voltage will drop at Balranal below 0.9 per unit. So if there is a contingency in the southern side, one of these other lines strip, more power will flow through this line, 220 kV line, and it will drop the voltage further. So what we do is we constrain the generation significantly. So lots of generation constraints are applied during the day. Lots of solar generation, in fact, in this area, especially in this Western New South Wales area, Southwest New South Wales area, to ensure system security.
Okay. Can you go to that slide with this fault right through? You have some graphs there.
This one?
No, on that one, yes. You can see now in the middle one that you can see the cycle is now the plant is riding through the fault and then picking up. The interval is about 4 seconds.
Yeah, it's repetitive fault right through. That is, a plant thinks it's this is megawatt, so you can see it's about from 0 to 50.
Yeah. So
what happens is, and then if you refer to voltage plot, you can see when at 5 seconds, this is a solar farm. Blue curve is a solar farm.
Why it is repeating in for 4 seconds to 4 to 5 seconds? Why it is repeating in a cycle?
Yes, what's happening is if you look at the voltage, around 8 seconds, voltage is very bad. You can see it because of that oscillation. Because when the solar is picking up, system interactions start and voltage is becoming very bad. So then the inverters see this as a problem. So inverter decide to shut down solar inverters. So it goes back to 0. You can see around 9 seconds.
Solar can do it, but the wind, the problem is how to dump the energy. You need resistors. Solar can disconnect. Yeah, solar can disconnect still.
Yes, but now
yes, not
only thing is
generate.
now, yeah, but we don't want this to happen in the system because this is causing, you can see the voltage. This voltage is not acceptable because you can see there's lots of flicker happening near 8 seconds and 9 seconds fluctuations. So this is not good for the other customers, especially mines in the area. They say they have very sensitive voltage sensitive loads or mine motors, drives and like that, they trip. Then they complain when these things happen. And then you have to pay compensation and like that. So you can't really let this happen. So what we have ended up doing is, in fact, what we did, we found a solution for this issue. We went and tuned these solar farm inverters. So we managed to get it over, and now we have the full solar farm and wind farm generating without any issue because solar farm inverters were tuned. They changed their inverter controls and power plant controls. So we managed to get a stable response after that tuning of the generation.
Okay, right. Thank you, Jahan. Right.
That's fine.
Nice to hear from
Any
you
other
after
question?
a long time anyway.
Yes, that's right. Nice to hear from you as well.
Yeah, okay. Good luck. Okay, take care. Bye.
Thank you all the best. Okay, thank you. Any other questions? Feel free to ask questions. It's fine with me if you can be online.
Dr. Jahan, are you also managing the what is the consequences of the rooftop solar PV into the national grid? Will there be any backfeeding, or have you seen such kind of things, or they are more or less localized issues?
Hello? Sorry, I think hello, can you hear me?
Yes, sir. We can hear you.
Okay, because I thought actually I mute myself now. Any other questions?
Are there any other questions from the audience?
Do you have any other questions? If not, probably.
It looks
Feel free to
like
ask questions. Hello?
Looks like we have covered all the questions, sir.
Okay,
Thank you so
then
much
that's
for
fine.
the enlightening session. And now I would like to invite Dr. Tushara Ratnayakar, the President of EESoc, to take over.
Madam, we can't hear you, madam. Madam, still we can't hear you.
We can't hear you, madam.
Sorry, I think there is some issues in Dr. Tushara's place. So anyway, so I am Prasad here. So thank you, Dr. Jahan, for accepting our invitation and delivering a nice talk to the students. I think it was a very good talk. And by the way, I think now it is late night there in Australia. So anyway, thank you very much. The present students, even though they do not have a chance to learn from you in University of Moratuwa, so we managed to at least give them a chance so that you could share your experiences and with our students. And also at the end, I know that you also shared some experiences as well as what the industry expects from the graduates. And I think everything was running very well. Thank you again. And also we expect your kind cooperation with us in future events as well. And thank you very much.
Yeah, thank you, Dr. Prasad, and thank you all for joining. And yeah, this opportunity, it's a great pleasure to do this talk. And yes, just tell me if you would like to do anything similar. Yeah, we can discuss any other topics if you would like to. And I can probably arrange others in over here as well. There are many others who would like to probably do similar talks. So let me know if you would like to arrange something. Thank you. All the best.
Thank you. Actually, it was very hard for me to find out your email to contact you. Anyway, now I got it done. So I will contact you again later to arrange some sessions.